Okay, guys. So I think last time, yesterday, we did it till here, and we'll start from basically the graph, and you can do this as homework. Very simple as it is. Anyway, so there's some features of the graph that we need to learn about. For example, the first point on the stress strain graph would be the limit of proportionality P, and then you have just after this you have elastic limit, and then you have just after this you have yield point, and the top point is ultimate tensile strength, and then the last point is the breaking point. Okay, so we're going to talk about this. So limit of proportionality P, you can always write it as a point beyond which Hooke's law is not obeyed. Okay, then you have elastic limit. Elastic limit is basically elastic limit is E, and elastic limit means a point beyond which a material does not return to its original shape after unloading. Right? Yield point is basically Y, this point, and in yield point you just need to remember the basically a point where beyond which the material shows greater strain for less change in stress. So we can say that the structure is rearranging. Like basically what happens is, like initially the material looks like this, and when you pull it, so it just stays like this, but after yield point the material can, now it keeps on slipping like this. So the structure is like changing. That's why it's showing you more change in length but less load taken or force taken, like that. Finally, you have ultimate tensile or compressive strength, but basically this is the point where material takes the largest load or largest stress, let's say. Okay, so if you look at the minimum stress that a material can take, so that's something, right? And then you have breaking point, and this is a point where the material fractures. So you guys need to remember this, okay? Like that. Anyway, now going to, like, you can write this down and then I'll go to the next question. Okay, if you guys have any questions, do let me know as well. Fine. Now, again, Young's modulus, we know it's stress over strain. And then one of the questions says that two wires of the same material and the diameter is d and the diameter q is also d. 2d, the same force F is applied to lower end of each wire. Show your working, determine the ratio. So you have the same force, and so you stress. In any ratio questions, you should make a table. Stress, force, area, because I know that stress is force over area. And the diameter is given, so I'm going to write diameter as well. The diameter of P is D, and the diameter Q is 2D. So the area you guys need to remember is pi by 4 D square, which basically means that area is proportional to D square. If something has like area A, then for a diameter of twice its size, it will have an area of 4a, because 2d square would mean 4 times the whole thing. Is it clear? Yes, people. You guys understand this? Any questions? Okay. So now you can simply use, like, stress in P would be force over area, and stress in Q will be force over 4 times area. And then because we need to take, we can divide this directly, or you can just simply write it as stress in P over stress in Q equals to force over area divided by force over 4 areas, and then just multiply. So it is going to cancel out. So this will come out as 4. You can write this 4. Please let me know if you have a question here. Okay, Hamad, Sultanat, Ryan, Javeria, Suhail, both Khatijas, Yaya, Laiba, everybody understands. Okay. Then it says strain. So we got to find strain now. Now for strain, we need like extension and length. The thing is that we got the length, but we don't have the extension, unfortunately. Yeah, that's the issue. So what we can do is, because they're made from the same material, we can use the Young's modulus to find this, because Young's modulus is stress over strain. So we can write Young's modulus, stress and strain, and then P and Q. So both have the same material, so Young's modulus stays the same. Stress in P was basically stress in P over stress in Q was 4, which means stress in P is 4 times of stress in Q. So we can write, if P has 4 times the stress of Q, we can write it like this, and we got to find the strain in P over strain in Q, like that. So now you can use the formula, like, strain would be stress over Young's modulus, right? So in P, the stress was 4 stress, Young's modulus was E. In Q, we got stress over strain and stress over strain, like that. So it's simple. So now again, we want strain in P over strain in Q, which will be equal to 4 stress over E divided by stress over E, and obviously it's going to be, so that would be 4 times as well. That's fine, right? Is it clear? Any questions now? So just make a table, and obviously it will help you, get most of it done. Anyway, so next we're going to talk about the next question. This sort of question where you will have a percentage. I intentionally did it because, anyway, stress is force over area, and strain is extension over length. You can also write change in length over length, so that's fine. So Young's modulus is 0.17 terapascals, and the cross-sectional area is given in millimeters. And the wire causes the causes the length of the wire to increase by this. Now, if you see a length of wire increase in percentage, that automatically means that it is strain, because the percentage increase tells you that it is like change in length over length times 100%. That's how it is coming here. Anyhow, so first of all, you got to find the stress. So stress will be force over area, and Young modulus is there. We don't have. Yeah, as I can see, we don't have like force, but no worries. We can use, Young's modulus equals to stress over strain, like that. Got to be 0.095%. So you can divide by 100 to remove the percentage sign, and you'll get it. I don't know why they've given it for 4 marks. I have no idea. So it's gonna be something like, I think, 1.62 times 10 raised to power 8 pascals. And then it says calculate the force, because stress is force over area. So you gotta find the force. Stress is 1.62 times 10 raised to power 8, and area will be pi by 4. Area is given, sorry. Area is given, so we're gonna write 0.18 times. Now we got to change this, right? We know that 1 millimeter is 10 raised to minus 3 meters. So 1 millimeter square, like you can square to both sides. So 1 millimeter square will be 10 raised to minus 6 meter square. So it's gonna be 10 raised to minus 6 meter square. So you multiply this, and that would give you the force multiplied by 0.18 times 10 raised to power minus 6. So that's basically about 29 newtons. That's the force cause it to move. All right, is this clear, everyone? Any questions? Let me know.
No, sir.
Okay, so then the rest of the questions are pretty simple. Like you can try this one with the table method as well. That's pretty easy. But this one I just want to I want you guys to do it with me right now. It says the Young modulus of steel is determined using a length of steel wire and found to have a value of E. So this is the Young modulus. Another experiments carried out using a wire of same steel, but the half the length and half the diameter. Which value is obtained for the Young modulus in second experiment? Can you guys tell me this, please? It has an answer that you should quickly like find it like this in a snap. Can you think about it? Read the statement again. There was an experiment on a length of wire. Yes, which had Young's
Is
modulus V.
it 2E?
2E. Who says that? Patija, is that you?
Live.
Okay, Laiba. Who agrees with Laiba that it should be 2E? Because it has twice the length, half the diameter. Yes, please.
Yes, sir, it's 2E.
No, it's not. If you see what you guys are missing out,
Sir, I think
half E. Okay, very good.
sir.
Yes, Hamad. Yes, Ryan. So what I'm saying is, the Young modulus you found was E in the first experiment, and it used the same steel. Same steel would mean that the Young's modulus remains the same. So it is basically material specific. And you guys need to understand that it has to be the same E. You don't even need to solve this question. You just need to understand that E is a unique value which is dependent on the type of material. So if the material is like steel, which is used again, it means it will have the same value. Do you guys understand this now?
Yeah.
Okay. Yes, Sultanat and Maham and Yunus, Vyaya, Ryan, Umar, Aman. Everybody is clear? Should I go forward?
Yes, sir.
Okay. Now, so this expression we derived yesterday, and basically, next thing we got to do is we got to find the area under stress strain graph, and I basically wanted to explain it through the question as well. So the question says an elastic material with Young modulus E subject to tensile stress S, Hooke's law is obeyed, and what is the expression of elastic energy stored per unit volume? So what you guys need to understand is that when you have the graph of stress and strain, oh my goodness, why won't you make this today? Okay, so you have stress here in pascals, you have strain here, and you have whatever kind of graph there is. So if you try to find the area under the graph, so you must understand that the area would give you half times stress times strain. Now do not assume that it is energy, because force times x graph is energy, but it's not. Why? Because if you open the formula, like stress is force over area and strain is x over L, so you might understand that on the top of it, like half times F times x over area times length. We can write, can I write it like this, please? So if you notice, this section basically tells you about strain energy, and this is the volume. So what you guys need to understand is that area under the graph of stress strain is energy per unit volume. Is it clear, everyone? Okay. Now, so going back to this question, it says that you need to tell us the expression that does that. So area under the graph would be obviously half stress into strain. Now in this question, what makes it different? Because if you notice, it has Young's modulus in them. So we got to somehow remove strain, and we got to find and put Young's modulus. Okay. So energy per unit volume is given by stress over strain, and strain itself is basically stress over Young's modulus. So what we can do is we can put it back into this, and we are going to get it as, like they have taken stress as S, so we'll take it as S over S E, like this. Okay, I don't think so. That's yeah. Wait a second. Yes, Sultana. That should not be correct. It should be half stress into strain. Okay, sorry. So I'm going to write it S, and then Young's modulus is given by stress over strain. So strain will be stress over Young's modulus. I'm going to put it here. So then it's going to look like half times stress over Young's modulus. So stress into stress will be stress squared over E. So that would mean that the answer that makes most sense would be A. Is it clear, everyone?
Yes, sir.
So do remember, again, I'm stressing it very, very much. Area under stress and strain graph is energy per unit volume. Okay, so they're gonna ask you this quite often. All right, then let's go forward and see what's stored for us next. So in this question, it says a metal wire is stretched to breaking point and the force extension graph is plotted. Which graph is correctly labeled with elastic region, the plastic region, and area representing work done to stretch until it breaks? Can you guys guess it, please?
Is it D? Is it D?
It is D. Very good. It is D because this region is still the elastic limit, so it has to be elastic. That is correct. And the rest of it like goes beyond that elastic region. And the work is done in stretching all of this. So right answers. Okay. So this is only like work done. This is for elastic potential because that shows that it comes back to original shape. These are like switched, and this is like entirely wrong because there has to be work here as well. Anyway, which is good, excellent. Now we're gonna move towards the graph of rubber and force extension. So when you stretch rubber or pull rubber basically behaves as a like it doesn't follow Hooke's law at all. So it has a line that shows when it is loaded with force and then it comes back with a different line. And the reason is that it loses some of the energy while doing so. So we're gonna learn how to find that. So first of all, I'd like to tell you that if you find the area which is this much, right? So in fact, it doesn't look nice, so I'm going to use the pens as well. So area under loading graph, like this. Area under loading basically shows you the total work done, right? Now, the area which is under unloading, which is this one, that basically shows you the energy recovered. This is the energy responsible to bring it back into its original shape. But then this energy that you see here in yellow, that is the area between loading and unloading, and that is basically energy dissipated as heat. Okay, if you guys know, you might know this, that in the game of squash, they basically first hit the rubber ball on the wall for a very, very long time to get it warmed up, because the wall keeps on, it deforms and then forms again, deforms, forms into the original shape, and then it becomes like the internal energy of it increases, because then it is playable. So it means the energy that is dissipated as heat is the middle part. So you guys need to remember that. All right. Any rubber that you keep on stretching, so you will notice that after some while it is going to get very hot. All right. Any questions here? Please let me know.
Sir,
Yes, Satanath.
so basically this line is cut, so how will we find the area until this?
Yes, that I'm going to tell you in the next part of this lecture, okay? Don't worry. I will tell you everything.
Okay,
So,
sir.
so you guys are done. You guys have shaded it and written the descriptions, please. Okay. Cool. So then, like she said, the question is here. See how much I listen to Sultanat. Sultan, are you proud of this?
Yes, sir. Thank
Okay.
you.
All right. So looking at this particular question, where they might give you a line like this, you have to use the estimation. All right. So estimation is done when you basically first of all find the area of one full box, which basically means if you look at like one box, it is like five from this side, five from this side, I believe. Yeah. Yeah, so it means that it's going to be newtons and that's in centimeters. So we will say it is 5 into centimeter will be like divided by 100, right? So it was going to be equal to, I think 0.25, but I'm going to just check 5 into 0.05, which is 0.25. Okay. So that would be the amount of energy in one complete box, okay? Then what you do is you count number of full boxes. This is just the way we have done it in kinematics as well. So this box is like almost full. No, let me just take it as half. This box is like almost full, so I'm going to call it 1. And then this box is 2. And then this one 3. This one 4. This is like almost full 5. And the rest of them meh. Okay, so then what I'm gonna do is I'm gonna write that the full boxes are 4, and then I'm gonna count number of half boxes. So half boxes you just need to estimate like this. So this one is like a half box, this is like one, and I'm gonna take this whole as half as well, and then I'm gonna take this small box as 3. Okay, then I'm gonna count this whole thing like although there are 3 boxes, but I'm gonna count this as 4. Like, sorry, I'm gonna count this portion as 4, and I'm going to count this portion as 5. I'm going to tell you why. And then I'm going to count this whole, like this portion as wait, I messed it up somewhere. Okay, I'm going to count this portion, this whole thing as half as well, so I'm going to call it 6. Now, why would you think, you would think why I have done this as 2, because then 2 and 3 can combine together to form one complete box. Do you guys understand this?
Yes, sir.
Similarly, like 5 and 4 can combine and 1 and 6 can combine. So when you combine them, they're gonna make almost one full box, right? So I'm gonna say that there are 6 half boxes which are equivalent to 3 full, right? So next thing I'm gonna do is I'm gonna find the total full boxes, and the total full boxes will be 4 plus 3, that's gonna be 7. And then if one box was of 0.25 joules, then 7 boxes will be equal to x, and you're gonna cross multiply. So 7 into 0.25, I don't know, and I'm gonna find this now. So it is 1.75, which makes it 1.8, and that's easiest way to do it. All right. The other way is that you can also make it like into boxes, but that would take more time, I believe, because then if you form boxes, right, then you will be looking at the readings all the time from this end and this end and this end and this end. So that would take a lot of time. I think that's difficult too. So that why. So I would recommend that you do the boxes method, and the examiner also, uses these answers by doing the same thing. Okay, is it clear, everyone? Any questions? Okay, so I'm gonna go to the next one, and in this question they've said that a metal wire has a constant kx, and they have this, and it says on figure 4.1 shade the area that represents energy S. Energy S is expanded to cause a permanent extension. So that would mean that it's talking about this whole area. So you got to shade it like this, okay, in your exam as well. Just shade it nicely. And then it says that use the figure to calculate this, right? And obviously this is again a curve, so you would have to sort of estimate it as well, okay? So I'm gonna give you this as homework because obviously, yes.
Still, there is this A part to this as well, right? For 4 marks.
Sorry?
Yes,
Oh,
sir.
oh yeah,
Yeah.
yeah, yeah. Sorry. My bad. I forgot about it. I did not see it. I thought I'd only posted B. All right. So it says show that for extension, strain energy stored in the wire is given by this. This is very easy. You make a graph here. Okay. You say it's force and extension, and you draw like a line, and then you say half times force times x, and then you say F equals to kx. You put it back into this, and you say, like, you can write it like this, and you can say I'm putting this here, and that will be E equals to half into kx times x, and that's going to be half kx squared. So 4 marks for doing nothing really. Okay,
Okay.
so that would be your this. Now it says suggest the change in structure of wire that causes the wire.
Question.
Yes. Yes, Hatija.
If it's energy expended, shouldn't it be only below the two lines in the graph? Rather
Where
than,
does it say? Energy
in part-
expended. Oh, yes. I'm sorry about that. I'm really sorry about that. I thought it was asking about the total work done. Fine. That would be this one then. Okay. Still, you need to use the boxes method to find it, Khatija. Okay.
Okay, sir.
All right. Then they suggest the change in structure of wire that causes the caused by the energy. So the change is that basically the layers of molecules slip past each other, right? Like I showed you. So especially in metals, right? Metals are like not very brittle. Some solids are brittle, um, glass. So when you pull a metal, so what happens is that between the layers, the slippage might occur. Like they might become like this, okay? And this is the reason why they're going in prosthetic deformation, they are losing like the shape because the layers of that structure are like moving past each other like this, okay? In elastic deformation, what happens is when you pull them together, right? So the molecules just go a little bit away from each other. So it seems like they've elongated, but they do not leave their original sort of structure. So it's when they go under yielding, that's when the slippage is really occurring. Is that clear, everyone?
Yes, sir.
Okay. So then you will also see these kind of graphs a lot. If you see the first kind of graph, they're going to ask you what is happening, or what is like which represents elastic and plastic deformation. So this is basically the elastic deformation, because although the line has bent, it stopped following Hooke's law, but because it comes back from the same line and to the same point, that means that it's basically um, has not exceeded elastic limit. Okay, that is a clear indicator of this. However, if it goes like here, but after you remove the force, it still shows some permanent extension here. Okay, go back please. Okay, so that would show a plastic deformation, which means that after unloading means when you remove the load, after unloading the material still shows deformation. Okay, that would mean that it has now gone beyond elastic limit.
Sorry?
Yes.
So in the first graph, you can say that it's reached its limit of proportionality, but not the elastic limit.
Yeah, it has exceeded the proportionality. That is correct.
Okay.
And this graph also tells us how we can differentiate between basically something like limit of proportionality and the elastic limit. So most of the people think that they're same, but that's not true, because elastic limit is like when after that the deformation happens, and even the in the rubber graph, it never follows limit like proportion of Hooke's law. So there's no limit of proportionality, but it never has crossed the elastic limit as well. So it comes back to the original shape. Do you understand? So for a material, it is not like 100% okay to follow Hooke's law, right? So it's all right, but it will always have a point after proportionality that will show you elastic limit. Anyway, so for a question like this, it says a long thin metal wire is suspended from a fixed support and hangs from blah blah blah. So where on the graph would the elastic limit be found? Can you please tell me that?
Anywhere before S?
Anywhere before, between R and N. Yeah,
So just beyond point S.
just beyond point S. Yes, that is correct. Because you see, Laiba,
Sir, I have a question.
you didn't understand the question?
No, sir, the answer.
Okay. Yes, what is the answer? What do you think is the answer?
Point T.
No, A is wrong. A is 100% wrong. Because what you
Sir,
guys.
D.
D, exactly at point T?
Yes.
No, that's wrong. That's wrong. I'll tell you why. You see that S is the limit of proportionality. Okay, Laiba? Now, I just said that till the line is straight, it is basically force is proportional to extension, it's following Hooke's law. But elastic limit always comes after that. You get it?
Yes.
So A cannot be correct. Okay, now why C cannot be correct? Because elastic limit can never be the same as limit of proportionality. That's what I said just now. So that's wrong. Why it is not point T? Because if this would have been point T, then it should come back to the same line because it has not crossed that point. You get my point?
Sir, can you please repeat this again?
Yes, what I'm saying is why it cannot be point T is if it was point T, then according to the definition, it says elastic limit is the point beyond which it shows plastic deformation. So now we have just reached that point. It means if we unload from this point, it should come back from the same line. Why is it going this way? Do you understand?
Okay.
So that would mean that the elastic limit has to be somewhere between this. Is it clear? somewhere in the middle. That is the reason that this has to be correct. Is it clear? Okay. So we're gonna go to this one then. So now I just want to do these different variant questions because obviously they will help you understand a few things. So in this one it says use the figure 5.1 to determine the Young's modulus of copper. Now a figure which is not a straight line, it curves at the end. So you will always understand, you have to understand that only find gradient of straight line from origin, okay, for E. Now why not this portion? Why not this portion? Because here E will change because the material shape is like now structure is changing, so obviously its stiffness will also change. So do remember that, do not find E from here. So you gotta only find E from this section only. Now it's super easy, you can take any point you want to, it's up to you. So I would generally want to take a easier point, and I think this one is quite easy for me. So I'm going to go here, I'm going to go here, and the strain is 1.0 times 10 raised to minus 3, and the stress is 1.1. So stress is 1.1 times 10 raised to power 8, as you can see. Now just simply write it down. You can say Young's modulus will be stress over strain, so 1.1 times 10 raised to power 8 divided by 1.0 times 10 raised to minus 3. So that I think will be 1.1 times 10 raised to power 11 pascals. Is it clear, everyone?
So would it be incorrect if you found the gradient by taking like two values for both stress and strain and doing how you would usually like y2 minus y1 upon x2 minus x1?
Yes, I'd like to do that, but because I need to be smart and I need to understand that this point will always be 0 and 0, no matter what. That's
Right,
all.
okay.
So I can only take one point in these graphs. Even if the graph was like they wanted me to find k, because I know the graph will start from 0 and 0, so I will just take one point and then do a force over extension to find k. That's it.
If it doesn't go through the origins, should you still take two?
Yeah, yeah. If yeah, I know. Sometimes what they do is they will give you a question like this. It will be like 4, it will be 2, and maybe like f and x, and a straight line. If there is extension, I'm not talking about original length, but if there is extension, you can take any point and then do force over x. That's it. You don't need to, because they have given you half the graph, and that means the real graph would have started from somewhere else. Is it clear?
Yeah. But sir,
Yes.
let's say the graph is like a y is equal to mx plus c graph, and since
Okay.
it doesn't go through the origin at all, then you will have to take two different values,
Yes.
right?
That is only when you will have force and length here and not extension. That then the graph would seem like this. And then you have to take 2 points. That's correct.
Okay.
Anyway, now, so keeping that in mind, then we're gonna go to this. It says sketch a line to show the variation of stress and strain of the rod as the stress is reduced from this to 0. No further calculation is expected. Sketch a line to show the variation with stress strain of the rod as. What does that mean? What does it mean? I don't know. Sketch a line to show the variation with stress and strain of rod as the stress is reduced from 2.5 10 raised to power 6. Okay. Alright, so this point. So when it is reduced, right, because it has already undergone some sort of, this. So what you're going to do is you're going to make a straight line, like this, and just let it be. Because basically when you go beyond elastic limit like it has, it just leaves a permanent deformation forever till this. So, and how do you know that you want to take it down or this way or that way? So basically the it will always go down parallel to this. So this line should be parallel to this, and you will see this in this question as well. Like in this question you see parallel lines, in this question as well parallel lines. Is it clear, everyone?
So does it have to come back to 3?
No, I just try to make it as a parallel line just by looking at it. Okay, it could be like here and there, it's fine. Okay, so by eye it should look like that you guys have drawn a parallel line. Anyway, then says the walls of tires on the car are made of rubber compound. The variation with stress or strain of specimen of this rubber compound is shown. As the car moves, the walls of the tire bend and straighten continuously. Use the figure, explain why of tires become warm. So you guys need to understand that you're gonna say when doing work, okay, sorry, when work is done on tire, it bends. Okay, when work, when it recovers, so when it recovers its shape, it straighten ups, it straighten up. Okay, okay, wait, straighten up. Okay, during this, not all energy is recovered. All right, so the area between loading, which is this one, okay, and unloading shows energy like heat being dissipated. Is it clear, everyone? Like that. Okay, especially for people who like to go on long drives, I just want to tell you something very important. So usually there is a set amount of, like cars have to be filled with air in their tires according to the temperature that is outside. So in summers, you need to keep the air pressure inside the tire less, because when the tires move, right, so they're continuously deforming and then coming back to their own shape. This causes the tires to get heated up and the air inside to get heated up as well. And if you fill the tire with a lot of air, so the temperature of the air rises, and then obviously it will collide more, increase the pressure inside, and obviously then your tire might burst. Okay, so you always check your air, make sure in hotter days you keep it high, like keep the air pressure low, and in cold days you can keep it high for a smoother ride, I guess. All right, anyway, so then in this question it says, which force extension graph shows plastic deformation of sample of materials? Yes, please, who can tell me?
D.
Yeah, it is as clear as D, because all of them come back to the same shape. Then says, which area represents the work done to stretch the sample?
In the Q plus R.
Yes, excellent. It has to be Q plus R. Anybody who has a different answer in mind that I can, clear your concept there?
No, sir.
Okay. Finally, we are done with this chapter. Yay! Okay. Now, since we're done with this chapter, tomorrow we are going to start off with waves, which is, I think, the second last unit that we got to do. But keeping, half an hour as a added advantage, a lot of people go through, like they have done practicals with me, but I would like to explain a practical question, and then whenever we have time again, I will explain another question, like question 2 as well. So today, let's open up a sample paper that you guys can tell
Sir,
me.
sometimes we have doubts in using the apparatuses.
Doubts in using apparatus. Well, the practice is not about using apparatus at all. Let me tell you that. So I will explain question 1 today and tell you when and how you should be dealing with that. So let's open the specimen paper, okay? Specimen paper 2022. And then we are going to talk about that, and then let's understand how we can come up with the best